Quickly, model misspecification errors. This could be a big topic, but I think in this context, what you need to understand is the model has assumptions, and those assumptions are in the background. I have put in here a very well-known example from 50 years ago by someone called Anscombe. This is artificial data. What he did is he created 4 very different data sets. If you use these data sets and estimate a model, a regression model, they all give you the same answers. They all give you the same answers. So in the first 3 sets, X is same, but Y varies in all of them. They are different between the different cases. Obviously, what's the message here? What he tried to show is, if you are not careful, you could end up drawing a model that's completely useless and doesn't even come close to describing your data. Why? Well, you can see the model in here in the first case is appropriate because that seems to be how the data are laid out. The equation is a good way of describing how y and x are relative. But if you go to the second case, you clearly see this is a nonlinear model, perfectly nonlinear. You estimate a linear model and you think you have done a very good job. The R-square value here is 67%. Obviously, that's a completely useless model because it's the wrong equation. In here, the correct model is linear, but unfortunately you have this one outlier. It could be someone just mistyped a number. And then you end up with this model that's linear, but misses the relationship because it's telling you the wrong story. And the worst is case 4, where there is no relationship between x and y. Y is varying here a lot. Nothing is happening to x. It's not caused by x, it's something else. But there is this one outlier. If you, without knowing your data, estimate a regression, which you wouldn't if you knew this is what's happening, then you would end up believing that you had a very good story. And you would be telling stories about how x affects y, and so on and so on. The main message here is be careful. Know your data, and that's what we say again and again. The model has assumptions. In general, if the model satisfies its assumptions or the assumptions, which we have listed here, linearity and zero mean error, homoscedasticity, which means the variance for the errors doesn't vary, and there is no serial correlation, and your explanatory variables are not related to the errors, then the Gauss-Markov theorem applies to your model. And what does the Gauss-Markov theorem say? Well, for a multiple regression model, if the regression model satisfies assumptions A1 to A5, then the least squares estimators are blue. Now, blue means best linear unbiased estimators. Best means among all linear. Now, we are not going to go into what linear estimator is. We'll leave it aside for now. It has the best standard errors. It's more precise, smaller standard errors. So when you estimate something, it's good to know what the point estimate is. But if the standard error is huge, and you have to consider that it could be something that gives a very wide 95% confidence interval, that method isn't very useful, because there is no point in me telling a farmer, well, the effect of nitrogen on yield is every kilogram gives you 6 kilograms of extra yield, when I know the standard error is huge, that number could be between 2 and 10. What I would want is a model that would give me an estimate, but the standard error is very small, which means my 95% confidence interval is very small. If I could tell the farmer that the expected extra yield would be between 5 and 7 kilograms 95% of the time, I am more precise. So best means more precise, smaller standard errors for your coefficients. Linear, that's a technical thing. Linear means it's a linear function of y, but if you go back to the formula for how we calculate the intercept and the slope, the intercept was calculated by recognizing that the regression line goes through the mean, and it's the same with the slope term. They are linear functions of y if you go look at the normal equation. Unbiased. Your coefficient estimates are unbiased. What does that mean? This is in the context of imagined repeated sampling. Of course, any research is just a one-off research. You don't go back and keep sampling to do your research. It's one-off. But in the context of an imagined repeated sampling, You took samples again and again and again, and you applied your estimation method, which is the regression method, and came up with coefficient estimates. On average, the estimated coefficients would be equal to the true but unknown coefficients. If I kept taking different samples, on average, my intercept estimates would be equal to the true intercept, and my slope estimates would be equal to the true slope. And this is similar to the sample mean. On average, the sample mean is equal to the population mean. So this is the Gauss-Markov theorem. It's a confirmation that everything is fine if the assumptions are not violated. But the assumptions can be violated because you can have autocorrelation, you can have heteroscedasticity. Heteroscedasticity means that the variance of the error isn't constant. And because of these things, you can have complications. There are other complications. You can have variables that move together, and you cannot tell the effect of one variable from the other very well. So if I have a sample where the rainfall and nitrogen levels move together, so when the rainfall is high, well, farmers are encouraged to apply more nitrogen, so they apply more nitrogen. I don't have a very good chance of separating the effect of nitrogen from rainfall because they move together. How am I going to separate them? There is no amount of clever econometrics or statistics I can separate them. If the variables move together and that collinearity is very high, then I want to know how much of the change in y is due to one variable as opposed to another. Sometimes you can have models that include variables that shouldn't be there. Irrelevant variables, that can be an issue, but a more important issue is omitted or missing variables. So someone gives you data, biomass, and how biomass changes with vegetation and so on, but then there are other variables that are important. Okay? It could be temperature, it could be some other thing that has had to do with the background history of the sites and so on. You know that these variables are important, but you don't have them, and you have to do research. So in a lot of cases, people will do research knowing that some important factors are outside the model, and because they are outside the model, they are part of your error. So that can be also important. Measurement errors. Of course, if you are in science, you know about this. So when you walk into the greenhouse to measure something, you cannot assume your measurement is perfect. If I send two research assistants into the same greenhouse to measure something, they could come back with two different measurements. So does it matter that you have measurement errors? When does it matter? Okay, measuring the outcome with error is not the same thing as measuring the treatment with error. Errors in the measurement of treatments are more serious than errors in the measurement of outcomes, because the outcome value, if you have an error, just becomes part of your error in the model. So there are these things. Autocorrelation, again, autocorrelation. There is something called spatial correlation, which is more appropriate for science and environment because you can have yield levels being correlated across space or with infestation. But if you are in social sciences, you use data measured over time, like income, employment, and could be exchange rates and so on, or GDP. So in those cases, you would assume that things would be correlated over time, and they can be correlated. And the way correlation works is when the error is positive, then it tends to stay positive for a while, and then it drops and becomes negative, and then tends to stay negative for a while. What that means is, well, if the normal economic functions mean that the level of employment is supposed to increase in a certain pattern steadily, but that's not how the economy works. When things are bad, they become really bad, so you get a lot of underemployment. So your model is going to overestimate employment, but when times are very good, also you get the opposite. So there are tests and remedies for this, but the thing you need to know is your least squares estimates are still unbiased, but their standard errors are wrong. So hypothesis testing is a problem, but if you use robust standard errors, you will be fine. Okay, that's the only problem. We will skip this. There are ways to wash out the autocorrelation if you know its structure. Heteroscedasticity, which you have been doing in a different context with ANOVA and multiple comparison, is relevant to both social and natural sciences. In this case, for example, let's say this is income, and this is something that increases with income when there is very little income. This could be how often people eat out. Well, if you don't have huge amounts of income, then there will be only certain times it's predictable. You are not going to go out 50 times a year or something when you are a student or a postgraduate student. But then when you get more and more income, then whether you eat out a lot depends on your characteristics. So the variance is very high. So it's more difficult to predict. And what that means is your uncertainty about the relationship here is much stronger than it's here. So the error doesn't have the same variance. And there are many good examples you can come up with. We'll skip the student exercise for now. But what that means is your error variance being heteroscedastic or not constant means the variance of the coefficients are no longer given by the case you had for the Bayes model where heteroscedasticity is assumed out. It means there is a different formula. This can be done by hand, and in most cases you don't have to do that. First thing to remember is even with heteroscedasticity, your coefficient estimates are still unbiased. But like in auto or autocorrelation, the standard errors are wrong. So if you use robust standard errors, which is what's shown here, and you have been doing this automatically, that's fine. How do you look for hetero? Many ways. One is you should first examine your residuals, but there are tests. There is an old test called Goldfeld and Quant test. It just chops the data into 3 sections, takes out the middle, and compares the variance here and here. Very easy method conceptually. The test you have been using, BP test, is the Bush and Pagan test. And what it does is it uses the residuals and it tries to figure out if the residual variance depends on a bunch of variables. There is an exercise there. You can do this by hand. You can read through this. How do you deal with hetero? Well, sometimes by correcting the functional form, you can make it disappear if the problem was a functional form. You can also use, now this is the first time you have seen this generalized GLS instead of LS. There is a method of estimation more complex than LS, but that can estimate models with heteroscedasticity. A third way is if you know how your heterogeneity is created. The example I was showing you where the y values fan out around the equation, well, you can see there is some kind of proportionality between the variance of the error and y or square root of y or something. And then you can transform the model and make it homoscedastic. The last one, leave the coefficient estimates as they are because they are not biased. Then just replace your calculation of the variance, the standard errors, fix them, and that's it. Then you are done. There are more misspecification errors, but I will let you go through those on your own. You can read through them. I mentioned some things about measurement errors and so on, but we'll leave them there.